Hey everyone, this is Dr. Walker. In this video, I'd like to go over another example from v011 on freefall. This is a rocket problem. We have a model rocket launched straight upward with an initial speed of 50 meters per second. It accelerates with a constant upward acceleration of 29.4 meters per second squared, and we're going to assume that this is the net acceleration, that it takes into account gravity, until its engines stop at an altitude of 150 meters. How long is the rocket in the air? First thing we want to do is we want to picture what is happening in this problem. We do have a picture given here, but if you don't have one given, you have to be able to come up with it yourself. So what we have here is a rocket launched with an initial speed, so the V initial here, and it has a certain acceleration until the rocket fuel burns out at this altitude, and this is 150 meters. So what we have to realize is that after the engines stop at this altitude, the rocket is going to keep going, but now it's going to be in free fall and have an acceleration of negative 9.8 because it won't have the engines helping it go up anymore. It's actually going to go up, 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 but it's going to slow down until it stops and then falls all the way back down. So it's really important to draw a picture that shows that there are two different phases in this problem. One acceleration of 29.4 and then phase 2 with acceleration of negative 9.8. So let's write down what we're given for the first phase. Over here, phase number 1 here. We have an initial velocity of 50 meters per second. We have an acceleration of 29.4 meters per second squared. We have a displacement of 150 meters. We know that it has that acceleration for the full 150 meters before the engine stop. So what's our approach to this problem? Think about it and always feel free to stop the video. A good approach would be to figure out the time for phase 1 and then the time for phase 2 and add the two times together. So with that in mind, we have enough variables to find the time. We have to figure out which kinematic equation to use that has v initial, a, delta y, and time. So pause the video so that you can find it. Hopefully you found this equation. Delta y equals v initial times time plus 1/2 at squared. Now we have to solve for time. We will have to use the quadratic formula. I can write it on the side here, but it's your variable, whether it's x or t, equals negative b plus or minus square root of b squared minus 4ac over 2a. If you have a calculator that can solve your quadratic equations for you, that's fine. Just go ahead and specify that if you are working a problem like this. So when we plug in the numbers into this equation, we can rearrange the equation so that it looks like a quadratic equation, the square term and then the linear term, and then the constant equals to 0. So that means that what's in front of t squared is a, what's in front of t is b, and then the negative delta y is c. And now we can plug in the ABC into the quadratic formula. And I'll go ahead and define them so that then I don't have to rewrite the whole quadratic formula, but a is going to be 1/2 of 29.4. And then b is going to be 50. And then c is going to be negative 150. So plug these three values into the quadratic formula, and that will give you that time. Will give you two times, but you know the positive one is the one that matters since we're dealing with time, which cannot be negative. So the positive time that we get is going to be 1.98 seconds. All right, so I'll call that T1 for the time for the first phase here. Now we need to find a time for the second phase. You may be tempted to calculate the time to go all the way up and then all the way down. But as in the previous example that we did, we can just find the time from the red X all the way down to the ground in one step by remembering that all that matters is the displacement from here down to here. And we know that displacement from here to here is negative 150 meters since we're going down. That's our delta Y for phase 2. So if we think of it that way, just caring about the endpoints, we have the displacement, we have the acceleration since we're in free fall. We just need one more variable before we can find time. We can choose between v initial or v final. Now v final, when we reach the ground, is not equal to 0. We know it's going very fast. So we don't know v final. However, we could find v initial. Now v initial is not 50, right? V initial that we're looking for here would be, what do you think it would be, right? We had a v initial here, but then the rocket accelerated until it had a final velocity when the engine stopped. So whatever the velocity when the engine stopped, that's the same initial velocity when the engine stopped, right? Vf equals Vo. That's the transition between phase 1 and phase 2. So let's find Vf. We're still in phase 1 here. Let's go ahead and find Vf. What equation are we going to use? We can use a number of them since we have all 4 variables, v initial, a, delta, y, and t. I like to use the original variables so I have less rounding error. So I'm going to use the equation that has v initial, a, delta, y, and v final. Can you find the equation? It's going to be vf squared equals v initial squared plus 2a delta y. I'm going to use this equation to solve for vf. I'm going to take the square root of both sides. Now do note that when you take the square root of both sides, you do get a plus and minus here, but we only care about the positive velocity because we know it's going up at this point. So we're going to have Vf equals the square root. We're going to have V naught up, I'm going to put the numbers in here, 50 squared plus 2 times 29.4 times delta y times 150. Plug all of these values in. We're going to get 106.395 meters per second. So now we're done with phase 1 and we can move on to phase 2. For phase 2, we can now find a time. Let's write down what we know for phase 2. V initial is not 50 anymore, right? V initial is the Vf that we just found. So 106.395. And then we know we're in free fall. Since the engine stopped, we know in free fall the acceleration is always negative 9.8 meters per second squared. And then we said we know the displacement. We know we're going down 150 meters. The whole path doesn't matter, only the endpoints. So with these 3 variables, we can solve for time again. We're going to use the same kinematic equation that we chose here and define our variables the same way and plug it into the same quadratic formula. So we can use this again, we can use this again. Let me go ahead and define ABC so that you can plug them into the quadratic formula and solve for the time. A is going to be 1/2 of little a, so it's going to be negative 4.9, since it's 1/2 of negative 9.8. B is going to be initial velocity, 106.395. And then C is going to be negative delta y, so negative times negative 150 is positive 150. Going to plug these 3 numbers into the quadratic formula right here, and we're going to get T2, this is the second phase, is equal to 23.04 seconds. So now we know that our final answer, we're just going to add the 2 times together. T1 plus t2 will give us the total time. 1.98 seconds plus 23.04 seconds is going to give us 24.96 seconds. So that's our final answer for the total time in the air. So hopefully this helps you identify parts of a problem that may be in free fall and then other parts that may not be in free fall, and then figuring out how the two parts are connected so that you can use a variable from one part, you can use that variable in the other part.